Today we are going to talk about linear versus quadratic versus... So linear and quadratic, we're very familiar with these, or we should be. So the linear parent function goes through 0, 0. It has positive slope, and the slope happens to be 1, which means it goes up 1, right 1, up 1, right 1, up 1, right 1, which I wasn't being specific about that here. And do you remember what the equation is for our linear parent function? It is y equals x. And then, of course, sometimes you might see it written a little bit differently. Instead of y, f of x means the same thing. So sometimes you'll see f of x equals x. So this is the picture of the linear parent function. It goes through 0, 0. It has a positive slope of 1. It's up 1, right 1, up 1, right 1. This is the equation to the linear parent function, and sometimes you'll see it written like this because y and f of x mean the same thing. Okay, one equation that we see a lot when we're working with linear functions is slope-intercept form. And just to talk about slope-intercept form a little bit, the m stands for the slope, and the b stands for the y-intercept. Okay, and I'll come back and I'm going to add something to this in a little bit. So basically that's what we know about our linear equations, our linear functions. Okay, moving over to the quadratic function. I'm going to draw just a rough sketch of the parent quadratic. Its vertex is at 0, 0. It opens upward. And the very first thing that the quadratic function will do is go up 1, right 1. After that, it does other things. But the quadratic parent starts at 0, 0. It opens up, and the very first step it makes is up 1, right 1. Okay, our equation to our quadratic parent is y equals x squared. So what could be the other way we could write that? F of x equals x squared. Simply because y and f of x mean the same thing. Okay, now I'm going to write down our standard form for our quadratic, and we've been looking at this form lately. Ax squared plus bx plus c. We've been using this with our factoring and with our quadratic formula. I'm only going to talk about two of these letters. A. This makes the graph open up or down. So A makes the graph open up or down. A also affects the width of the graph. If A is a positive number, the graph will open upwards. Like in our quadratic parent, the A is a positive 1, which is why the graph opens upward. And then we've also learned that the bigger the A, the skinnier the graph, the more narrow the graph. And the smaller the A, like a 1/4, a 1/8, a 1/16, the wider the graph. Okay, and then C moves the graph up or down. So C moves the graph up or down. When the C is positive, the graph moves up, and when C is negative, the graph moves down. And B has a part in there, but that's all we're going to talk about for right now. Okay, exponential. We talked about this at the very beginning of the year, but we really haven't done much with the exponential graph. So I'm going to show you the exponential graph. It looks like this, and this is actually representing exponential growth. Later I'll show you what exponential decay looks like, but this is our exponential graph, and its parent is y equals ab raised to the x. And I'm going to go ahead and just write that same equation down here. So if a function is exponential, then that means the x is the exponent. Exponential, x is the exponent. So if you see your x as an exponent, then we're talking about an exponential graph. Okay, one thing to talk about here is A is our initial amount. It's what we start with, and I'll make this make more sense over the next day or so. So A is the initial amount, it's what we start with, and B is our growth factor. Ooh, can I squeeze that in there? So B is our growth factor. Okay, so as of right now, we're going to actually flip this paper over and we're going to write on the back of it. So you don't really see anything here. And on the back, I want us to write linear, question mark, quadratic, question mark, exponential, question mark. Some of this will be slightly review, but some of it's going to be new. So we're going to be looking at some tables. So I'm going to build a table. And I never really make anything extremely beautiful because I have too many other things to do in my life. So if you're okay with this not being beautiful, that's awesome. And if you're not, pretend. Okay, so I want to figure out if this table represents a linear function, a quadratic function, an exponential function, or none of those choices. So this is when we go through and we find the change in our x's and the change in our y's. And we've done this before. It's just a lot of times our table is vertical instead of horizontal. So how do you get from 0 to 2? You go up 2. How do you get from 2 to 4? You go up 2. How do you get from 4 to 6? You go up 2. Okay. How do you get from -5 to 1? You go up 6. How do you get from 1 to 7? You go up 6. How do you get from 7 to 13? You go up 6. Okay. To know if this is linear, I want to see if the change in my y over the change in my x gives me the same answer every time, because slope is y over x. So let's see. Does the change in my y, 6, over the change in my x, 2, do I get that the whole way through the chart? 6 divided by 2 makes 3. 6 divided by 2 makes 3. 6 divided by 2 makes 3. So yes, since I get the same slope, I get the same change in y over the change in x the whole way through the chart, the whole way through the table, then I know that this is linear. And I know that my slope is 3. And then from there, I could work on writing the equation of the line that represents this data, which we've done that before, and we're going to do it again later. So I'm not going to stress on that right now. Okay, let me show you another one. This one I'm going to make vertical, just to make it look a little bit different than the last one. Okay, so first I'm going to focus on the change in my x's. How do you get from 1 to 2? Up 1. How do you get from 2 to 3? Up 1. How do you get from 3 to 4? Up 1. Okay, in the y's, how do you get from -1 to 1? Up 2. How do you get from 1 to 3? Up 2. How do you get from 3 to 5? Up 2. Okay, let's see if our change in our y over our change in our x gives us the same answer every time. The change in our y is 2. The change in our x is 1. And do we get 2 over 1 the whole way through the chart? Yes, 2 over 1, 2 over 1. We get 2 over 1 the whole time, which is the same thing as 2. So since my change in my y over my change in my x is the same the whole way through the chart, then that's how I know that this is linear. And I know its slope is 2. And from there I could go on and I could try to write the equation of the line. Okay, and that does mean that both of these graphs are lines. Both of them had positive slopes, so they both would go uphill from left to right. Okay, another thing I want to point out, something I haven't really said in the past, and I want to focus on this today, is that if your x's ever go up by 1, 1, 1, I can look at this and call this the first differences, the first time I found the difference between these guys. So this is called our first differences. So first differences. So if our x's go up by 1 every time, and our first differences are the same, that's another way to know that it's linear. So you want to check to see if your x's go up by 1 the whole way through the chart. If they do, if your first differences are the same, then it's linear. So I want to add that on to the back side. Over here when we were talking about linear, I want to write that first differences are the same. So the first differences are the same. Okay, let's build another chart. I'm going to take this one back to being horizontal. So x, y, -2, 4, -1, 1, 0, 0, 1, 1. Oh, let's squeeze in another one. 2, 4. Okay, so let's take a moment and look to see, do our x's go up by 1 every time? Yep, the x's go up by 1 every time, so I'm just going to find my first differences. How do you get from 4 to 1? You go down 3. How do you get from 1 to 0? You go down 1. How do you get from 0 to 1? You go up 1. And how do you get from 1 to 4? You go up 3. These are called our first differences. Are they the same? No. So this is not linear. Okay, next I'm going to find the second differences. I'm going to find the difference between these guys. How do you get from -3 to a -1? You go up 2. How do you get from -1 to a +1? You go up 2. And how do you get from a +1 to a +3? You go up 2. See how the second time we did it, they're the same? When your second differences are the same, then that's when you've got yourself a quadratic function. So when second differences are the same, that makes this guy quadratic. And I'll show you later how we can write an equation for this. Right now I just want you to know how to know if it's linear, quadratic, or exponential. So if your second differences are the same, then it's quadratic. Okay, let's flip. So over here where we have quadratic, let's write second differences are the same. Okay, let's flip back. All right, let's try another chart. Let's make this one vertical, just to get used to looking at them different ways. So here's x, here's y. Let's go 0, -2. Let's go 1, -1. Let's go 2, 2, 3, 7, 414. Okay, first let's look at our x's. Do our x's go up by 1 the whole time? Yep, up by 1, up by 1, up by 1. Okay, so let's just find our first differences. How do you get from -2 to -1? You go up 1. How do you get from -1 to 2? You go up 3. How do you get from 2 to 7? You go up 5. How do you get from 7 to 14? You go up 7. Are my first differences the same? No. So let's find the second differences. How do you get from 1 to 3? You go up 2. How do you get from 3 to 5? You go up 2. How do you get from 5 to 7? You go up 2. Since my second differences are the same, then I know that this is quadratic. So when the second differences are the same, then we have ourselves a quadratic function. When I look at number 5, let's make another chart. So let's start with x and y. Let's go 0, 3, 112, 248, and 3, 192. Ooh, got some big numbers here. All right, if you couldn't see all those. Okay, so looking at this, let's see if our x's go up by 1 the whole time. Do the x's go up by 1 the whole time? Yes, they do. So let's find our first differences. How do you get from 3 to 12? You go up 9. How do you get from 12 to 48? You go up 36. How do you get from 48 to 192? You go up 144. Okay, the first differences aren't the same, so let's find the second differences. How do you get from 9 to 36? You go up 27. How do you get from 36 to 144? You go up 108. This one, my first differences aren't the same, my second differences aren't the same, so I'm going to check for something else. I'm going to check to see if I get the same quotient every time. So I'm going to look at my y's, and I start with this one. What's 12 divided by 3? 4. Now let's start with this one. What's 48 divided by 12? 4. What's 92 divided by 48? And that's 4 also. So when you get the quotient of the y's to give you the same number every time, that's when we know that we have got ourselves an exponential function. So this one is exponential. And I'm going to actually show you how to write the equation to this because it's pretty easy. Okay, A, we said earlier, is our initial amount. I always want to look for the 0 for our initial amount. So our initial amount is 3. B is the growth factor. That's what we're growing by every time. And that's what we get when we find our quotient. So we're growing by 4 every time. And that is the equation to this exponential function. Okay, let's try one more. And I'm going to make this one vertical, just to practice that. So xy, 0, 100, 150, 225, and 3, 12.5. Okay, so first I want to look to see if my x's are this, if the x's go up by 1 the whole time. And they do. The x's go up by 1 the whole time. So let's find our first differences. How do I get from 100 to 50? Down 50. How do I get from 50 to 25? Down 25. How do I get from 25 to 12.5? Down 12.5. Okay, first differences aren't the same, so this is not linear. Let's check our second differences. How do I get from a negative 50 to a negative 25? I go up 25. And how do I get from a negative 25 to a negative 12.5? I go up 12.5. Okay, my second differences aren't the same, so this isn't quadratic either. So now I'm going to check to see if it's exponential. So this is when I start looking at the ratios. I look at the quotients. So over here, I'm going to write down ratio. I'm going to write down quotient. They mean the same thing. Ratios, are they the same? Quotients, are they the same? So I'm going to start with this y, 50 divided by 100. And 50 divided by 100 makes how much? 1/2. Then I'm going to go to this y. 25 divided by 50. And 25 divided by 50 makes 1/2. And 12.5 divided by 25, that also makes 1/2. So I know this is exponential. And then I'm going to go ahead and I'm going to write my equation for this, which is in the form y equals ab raised to the x. Let's see if zero's in my x in my table. It is. So this is my initial amount. I start with 100 of something. So y equals 100. B is the growth factor, and it's a 1/2. That's what I got when I found the ratio. So actually, this one is called exponential decay, but we'll talk about that more later. So this one over here is exponential growth. This one over here is exponential decay. But that is how you basically tell if something is linear, quadratic, or exponential. I just want to add one more thing over here on the back side. So with our exponential, I'm going to write ratios are the same. And later I might say this a little bit differently to help you a little bit more. So I want to see if ratios are the same. Well, I shouldn't have a question mark there. Let's make that an exclamation mark. Ratios are the same if it is exponential. Okay, and that's all. Smiley face.